Welcome. In this video, we are going to focus on diffusion models, especially on this paper that focus on making diffusion sampling faster. So that's the PNDM sampler. That's one of the most commonly used alongside DDPM on DDPM solver. We've implemented both of them in previous videos. So if you have not seen them yet, I would invite you to have a look at those videos. But yeah, let's dive into this video. These are the results we'll get by the end of this video. So basically, this is about sampling. Basically, what we're going to do, we're going to take a model that was trained from scratch, a model that was trained with DDPM. So basically, that's the code that we used. That was also covered in another video. These were the samples we obtained, each of them using 1000 function evaluation. Now what we do, we reload this model that was trained using DDPM, but we do sampling with the sampler from this paper. And basically you can see that we get about the same sample quality, but we do that in a much fewer function evaluation steps. Sampling is about 50 times faster, so that's a huge gain, especially if you need to sample many images. For example, if you need to do compute FID, or if you need to deploy your model, you want it to be fast. So yeah, let's dive into the code on these are the results you should expect by the end of this video. So we start by implementing the diffusion model. So far, these are just a standard or general parameters. So big T is the number of time steps that you use during training. You discretize T, and you take the function approximator, so the neural network that will be used for denoising. Then you have all the variables related to the variance schedule. So yeah, beta, alpha bar. And then we can implement the training API on the sampling API. So basically here you see that we do not implement them. I just add them here for the sake of consistency. It's because we built upon this code from DDPM. And basically if you wanted, you could just keep those functions. Or another way to say it is that here we are just going to use to add additional function to this code. So basically we are going to use to add this new sampling function so that you can sample from this model in a much faster way instead of just using 1000 function evaluation here. Okay, so then you can put everything together and you can train everything with the full code. Okay. So now we move on to the interesting part, the PNDM sampling. We try to stick to the sampling API so that we can easily switch from one function to the other. We just add an extra parameter, number of steps. By default, the sampling function use big T, so 1000. But here, using this algorithm, we can use, for example, only 50 time steps. So basically, we make sampling 20 times faster. Basically that's the algorithm too in the paper. We can maybe have a look at it, but basically our implementation will be straightforward. It will be a straightforward mapping from the pseudocode to the code. So yeah, we just compute the step size. So basically we divide big T by the number of steps to have the step size. Then we compute all the step size from 0 to big T using the step size. Once this is done, we compute the first value of X, so basically the noise. We sample from Gaussian noise, and then we will iteratively denoise this value. Here we have an epsilon buffer on a counter. Okay, maybe we are going to come back to that later. We'll explain those variables later. We create an iterator, so basically we'll iterate along our time steps. So basically at every iteration, we have two values, T and T next, and we use zip to do that. And we add TQDM on top of it if the users want to use it, but otherwise we do not use TQDM. So if the users want it, we add a progress bar, and if not, we do not add it. On here, we can see it's a direct implementation of the pseudocode. If T, or let's say if our counter is greater than 3, we use PLMS to get XT on epsilon T, and otherwise we use PRK. On why there is this if-else statement It's because to do this PLMS step, we need, it's a recurrence equation, so we need the three previous epsilon. But at the beginning, of course, we don't have them, so we are going to use another algorithm. It's based on range QTA, so well-known algorithm in standard algorithms. It's a standard algorithm well-known in computer science. So basically, the first three epsilon, we get them with PRK, so range QTA, and then we are going to use this equation 13. That's a recurrence equation, but that needs the previous three epsilon value. Okay, and that's why basically we have this epsilon buffer. We need to track the latest three value of epsilon. So at every step, we add epsilon to the buffer, and we only keep the latest three. So if there are more than three values in the buffer, we remove the first one. Okay, and then we can just return x. So basically, this algorithm, very easy to implement, just straightforward implementation of the pseudocode. But now we need to dive in a bit more into this PRK function on this PLMS function. Okay, so we are going to do to start with PRK. Basically it's the opposite. So it's for this equation 12, that we need the three latest value. But for equation 13, you just use range QTA. You don't need the latest three values. It's just the opposite of what I said. So okay, let's start with equation 13. So basically we compute, we have t next, and we need to compute the t in between. So we compute the delta between t and t next, and we compute tm, so t in between. So the t that is between t and t next. So basically we have t next and tm, t in between. These are integers, so we convert them into PyTorch tensors, and we adapt the shape with respect to the batch size. And then we can just do a straightforward implementation of the equations. So basically we just implement those equations. You see that there is a phi function that we are going to implement later. I think it's maybe the equation is in the appendix. Okay, I'm not sure where it is in the paper. We're going to come back to it later. I know that in the comments we know the equation number, but basically for now we assume that phi is implemented. We're going to implement it in a bit. And I like to implement like this. To really start with the high level, like I did here, I assume that I know the functions. So I'm doing my code, I'm implementing every high level function, and then little by little I dive into the function. And I feel it makes implementation much easier and much faster. Okay, and once I have all those variables computed, I can combine them. Again, I'm just following equation 13. I'm combining my epsilon, and I'm computing the next x. Okay, x next. So now that we've done PRK, we can do PLMS. So equation 12, so you can see it's much easier. First, you run your function approximator to get epsilon t, and then you combine epsilon t with the three latest values. And again, you use the phi function to get x next. So basically, we just convert that equation into code. Again, we need to convert t, which is integers, to a PyTorch tensor. On here, just straightforward implementation of the equations. Finally, we can implement the phi function. Okay, it's section 3.3, equation 11. Okay, basically that's the phi function. So it seems quite complex, but yeah, we just need to implement it. That's a combination of xt and epsilon t. We just need to implement it and make sure we don't make mistakes in our code or in the writing of the equation, on the priority of the operations, on things like that. So yeah, we compute alpha bar t for this current time step t. We compute alpha bar next for the next time step t. And then we can just plug everything into the equation. And basically, we've done most of the work. Again, here I'm really focusing on the implementation and not the theory. If you want me to do more videos about theories, about paper review, just let me know. But yeah, now that everything is implemented, we can reload our function approximator that was trained with the DDPM approach. Then we can create our diffusion model. on fidelity, the function approximator, we can use our sampling function. We want to sample 81 images, and then we can just use matplotlib to make this grid of images, and you should get results like those one. Okay, I really hope you like this video. If it was, please leave a thumbs up, leave a comment, even a very basic comment. It really helps with the algorithm. Subscribe, and see you in the next video.